students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can try to help in some way or another. So lucky you, you get to hear my voice for another lecture. But the best part is we will be learning how to estimate population means with confidence intervals. Yay! In the last video, we discussed how you can also use the central limit theorem for a sampling distribution of means. Just like when we talked about proportions, there are certain conditions that need to be met. First, the sample must be random and independent. The sample size has to be large enough so that the sampling distribution of the means will be approximately normal. Finally, the population has to be at least 10 times larger than the sample size. Unlike when we're checking conditions for the central limit theorem when we're working with sample proportions, for this course we're just checking the criteria for random and independent samples and that the population is at least 10 times larger than the sampling size. I'm going to emphasize this again. The whole idea with statistics is that we're trying to make an inference about the parameter, some statistic of the population. The parameter is the truth. It's what's actually happening within the population. But since we only have access to samples, we can only infer what's happening. We can never be 100% sure of the truth. One way to be closer to the truth is to increase the sample size. That's why the sample size is so important when we're trying to estimate proportions or means. The bigger the sample size, the closer we are to the size of the population, and the closer the sample statistic is to the population parameter. In terms of standard error, the standard error will be smaller if we have a larger sample, right? The larger the sample, the less error. As the size of the sample starts to get closer and closer to the size of the population, the standard error statistic decreases and decreases and decreases. At the point where the size of the sample is the same size as the population, the error goes away. We actually know the truth. Will be equal to the population standard error parameter. They'll be the same. You're working with the same size. When we select simple random samples of whatever size n we have, then we can use this formula in order to calculate the standard error. In order to do this, we have to have the population standard deviation. Without the population standard deviation, we cannot calculate the standard error for this particular sample size. Three videos ago, I think, we started talking about confidence intervals when we were talking about estimating where the true population parameter would be of a proportion. And if you recall, the confidence interval gives us this range, which is encompassed or captured by a lower bound and an upper bound. And within those two bounds, the lower and the upper bound, is a range of values that are plausible for the population parameter. The confidence level gives us a level to express how confident we are that the interval actually is contained within the population parameter. The larger the confidence interval, the wider the range of plausible values. So let's quickly review the relationship between confidence levels and interval width. Let's just say that this is your unknown true value, the population parameter. And it looks like it's somewhere between 130 and 145. Let's just say it's at 135 or so, okay? We can't see this. So imagine if this red thing was covered up. Make a best guess of where that would be located here. Using our sample, we could calculate a mean. And then we can use a confidence level to give some degree of certainty of how likely that sample mean is to be true. So for example, let's say that this is my scale. I took a sample, whatever size, and my sample mean is 100. Then I decide to use a 68% confidence interval level. I am basically saying that I am about 68% certain that although I do not know the population parameter, I am approximately 68% certain that the true population parameter exists within 85 and 115. Now, as I increase the interval width, I take up more of this number line. So what I'm saying with a 95% certainty level is I can say with 95% certainty that the true population parameter is within 70 and 130. Okay? In this situation, I'm still wrong, but I'm giving myself more of a range in order to capture the truth, not knowing what the truth is. If I were going to say I am 99.7% certain that the true population parameter exists somewhere between 55 and 145, then I have captured it. I've captured it because my interval width keeps getting longer and longer. I'm capturing more of all the possible values. Here, with 99.99 degree of certainty, I'm saying I'm very, very, very sure that somewhere within 40 and 160 is where the true population parameter lies. I don't know what it is. I think it's 100, but I know that I can't be 100% sure, but I can be 99.99% certain that it is between 40 and 160. I'm covering myself by using this longer and longer confidence interval, so I'm less likely to be incorrect about where the true population parameter is. So by now you've been seeing these numbers 68, 95, 99 over and over and over again for several weeks, right? You've seen them over and over again. And you know that they come from the way that probabilities exist under the normal curve, or the area under the normal curve. So this model tells you that within one standard deviation before and after the mean, 68% of the values lie. Within two standard deviations before and after the mean, approximately 95% of the values lie. Approximately 95% of the values lie. And within three standard deviations before and after the mean, approximately 99% of the values lie. So this is where these percentages, probabilities are coming from. When we first started working with probabilities under the normal curve, we used these anchor z-scores. We used 0, positive 1, positive 2, positive 3 as we worked over to the right as values increased. And if we looked to the left of the mean, we saw that the z-scores were -1, -2, -3, -4, and they were describing the relationship between z-scores and values that are less than the mean. When we used these anchor z-scores originally, these were estimations. We did it just to simplify things as we started to get more comfortable with statistics. But what we learned, 5 or 6 videos ago, is that these estimations, these numbers have been rounded, and with rounding we lose precision and we increase error. So instead of using positive 1, positive 2, positive 3, we actually are going to use values that are much more precise. So for a confidence level of 95, instead of using 2.0, we're going to use 1.96. Instead of using 3 for approximately 99, we're going to use 2.58. So what have we done? We've increased the number of places to the right of the decimal to become more precise and try to shave off as much error as we can. Okay? Now, as you're working, a good practice is to not round anything until you get to the very end. So if you round your confidence level multiplier, these are called multipliers. If you round your multipliers and then you round your standard error and then you round your lower bound and your upper bound, every time you round, you get more and more and more error. So it makes it really difficult at the end to figure out exactly where all this error is coming from. And I think we see that in when we're doing like the tests on Blackboard. A lot of the times people have just rounded so much that the computer no longer recognizes the value as a correct calculation, even though you have gone through all the steps correctly. So that's why waiting until the very end to round is a really, really great practice. And another benefit to statistical computational software is that it doesn't round. It doesn't round until the very end, and it allows you to figure out how far you want to go out in the rounding. So these are more precise z-values that we're going to use to calculate confidence levels in the hopes of decreasing error as much as possible. So let's try some problems. These are the necessary materials that you will need. You will need a pencil, unless you're brave enough to do stats in pen. You will need paper. You will need a calculator. Google Calculator works great. And you will need technology for probability calculations. So let's look at our first example. This example has to do with restaurants. See my restaurant picture? Okay, so the population in question consists of local restaurants ranked by revenues. That's how much they earn. And you are trying to find out the average revenues for the restaurants on a list. Okay. The population standard deviation is $15,056.37, and a random and independent sample of 30 companies obtains a sample mean of $10,672.87. And they're wanting you to calculate the 95% and the 90% confidence intervals for the average revenues. All right, we can do this. Let's go to Ziteboard. Okay, so here are the restaurants, and let's see what we've got. Okay, so these are a bunch of local restaurants, so there's got to be a lot of them. And the population standard deviation is going to be $15,056.37. That's precise. And it's got a random and independent sample of 30 companies. And when they looked at the sample mean for those 30 companies, or those, sorry, not 30 companies, 30 restaurants, I guess, they found a mean of $10,672.87. And they want the 95% confidence level and the 90. Okay. All right. Well, first thing we have to do is it says nothing about the normality of this thing. So we need to make sure that we're not violating the assumptions of normality. So first we need to make sure that we've got a random and independent sample. And it says right here that we do. Where's my green? Because I like to use green. Random and independent sample. So check. All right. So that's done. Next thing is I need to make sure that my population size is at least 10 times bigger than my sample size. So the number of local restaurants needs to be bigger than 10 times 30. So that needs to be bigger than 300. And I would say that, yeah, there's at least 300 local restaurants in the city of New York. So, yep, so that fits too. Yes, okay. So now we can assume normality. Distribution is normal, and we can apply everything we know about the normal curve and the distribution, blah, 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 to this problem. Fabulous. Let's scooch this up. Okay. All right, so let's start drawing a model. Remember, you want to always draw the model. Take the time to do this. So that you have a very clear idea of what you've done and what you have yet to do. Okay, here are my anchor z-scores. And my mean, that mean is long. Okay. I'm going to scooch this up and make this a little bit bigger so I can write that giant number in here. 10,672.87. Okay. And I need to find this distance. So in order to find this distance, this is a sample, right? And we've taken this sample to try to make an inference about the population. So this right here is going to be my standard error. So my standard error formula for a sampling distribution of the means is the population standard deviation divided by the square root of the sample. So I have my population standard deviation is 15,056.37. And I'm going to divide that by the square root of my sample size, which is 30. Fantastic. So let me just grab my Google calculator. Come here, little Google calculator. Where are you? Okay, here you go. Okay, here we are. We're right here. Okay, clear, click, clear. $15,056.37 divided by the square root of 30, and my answer is $2,748.90. Okay, so that means that this distance right here is $2,748.90, and this is the same, 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 and this is the same. So I can add $2,748.90 to the sample mean, which is $10,672.87, and I can find the corresponding raw scores for this example. So this is this is gonna be fun. Okay, there's a lot of clicking going on here, but whatever. 10,672.87 plus 2,748.90 equals, and I get 13,421.77. Okay, I'm going to go ahead and add that amount again, plus $2,748.90 equals $16,170.67. I'll scooch that over a little bit. And then I'm going to add that one more time, plus $2,748.90, and I'm going to get 18,919 and 57 cents. Okay, great. Now I'm going to go in the opposite direction. 10,672.87 is my mean, and from that I'm going to subtract the standard error. So I'm going to subtract $2,748.90, and I'm going to get $7,923.97. Subtract it again. I get $5,175.07. 517507. And I'm going to subtract one more time. Oh my gosh, it's going to take longer than anything else. Subtract 2748.90 equals 2426.17. Okay, fantastic. So now I've got this all written out. I need to get my 95 and 90% confidence interval level. Okay, well, let me just run over here real quick and look at my multipliers. My multipliers are, so I've gone ahead and just jotted down my confidence interval levels that I needed right in through here. So here are my multipliers. So let's go ahead and figure out my confidence intervals for 95 and 90. Let's do 95 first. I'm going to do 95 in blue, 95% CI. Okay, so I'm going to take my mean and as my center value, and I'm going to calculate my margin of error by multiplying my 95% multiplier by my standard error. So let's do margin of error first. So here's MOE. For 95% interval, I have a 1.96 multiplier, and I'll multiply that times my standard error. So $2,748.90. I'm going to bring over my calculator right here, clear it out. 1.96 times 2,748.9 equals, and I get $5,387.84. So MOE is $5,387.84. 84 cents. Okay, great. So I've got my mean. My mean is $10,672.87. I need to add my margin of error over here to this number, and I need to subtract my margin of error from this number on this side. So I'm going to scooch this over a little bit. Okay, so and my margin of error is 5,387.84. So here I have 10,672.87 cents, $5,387.84. Clear this out. $10,672.87 plus 5,387.84 equals $16,060.71. Okay. On this side, I'm going to take the $10,672.87 and I'm subtract the $5,387.84. Okay. Bring this over. Clear, clear, clear. 10,672.87 minus 5,387.84 equals, and I get $5,285.03. Okay, so what does this say? For this particular 95% confidence interval, it says that according to this sample, you believe that the mean revenue for local restaurants is $10,672.87. But you can say with 95% certainty that the true population proportion is somewhere between $5,285.03 and $16,060.71. Okay, now let's do the same thing, but this time we're going to do it for 90% confidence interval level. And this one I'll do in red. Okay, now 95 is a wider interval than 90. So this number is going to be greater and this number is going to decrease because the interval is going to get more narrow. It's going to get smaller. The width is going to get more small. So let's see, I've got 90% CI And I'm going to go ahead and calculate my margin of error like I did here. Margin of error is my multiplier. In this case, it's 1.645 because it's 90% interval level. And the standard error is going to remain the same, $2,748.90. So I'm going to bring over my calculator. Clear, clear, clear. And I'm going to go ahead and multiply these together. 1.645 times $2,748.90 equals. Okay, so here I get my margin of error is $4,521.94. Okay, we're going to scooch this up. My mean is going to stay the same. The average for those restaurants that we looked at their revenue and averaged out is the same. On this side, I'm going to add the margin of error, and on this side, I'm going to subtract the margin of error from the mean. Okay, so my margin of error was $4,521.94. So this side is going to be $10,672.87 plus $4,521.94. And if I bring over my calculator, I have $10,672.87 plus $4,521.94 equals $15,194.81. Okay, and on this side, I'm going to take my mean and I'm going to subtract the margin of error. So here, I'm going to clear this out. 10,672.87 minus $4,521.94 equals, I get $6,150.93. Okay, so now I can say with this is that according to our sample of 30 local restaurants, we calculated the average revenue for those restaurants to be $10,672.87. Based on our sample, we believe that this is also the average revenue for all local restaurants. However, since we only have a sample, we can say with 90% certainty that the true population mean is somewhere between $6,150.93 and $15,194.81. Now I want you to notice something. I'm going to zoom this out a little bit so you can see it. Hopefully this is easy to see. Here, when we had 95% confidence interval, the 95% would take a larger range, right? 95 is a wider interval. So the margin of error is 5,387. Here, 90% is a more narrow interval than 95% confidence interval. Notice that the margin of error is 4,521. It's less than it is for the 95. The margin of error added to the mean and subtracted from the mean is going to be what actually causes the interval to be wider or more narrow. Since the standard error is the same for both interval levels, it's this multiplier that is really causing the interval to be wider or more narrow. As usual, I have gone ahead and written the steps out here in the Google slide presentation that is linked in the description box below. Also, the Ziteboard will also be in the description box below. Okay, so let's try this with StatCrunch. So we're going to go ahead and go into StatCrunch and follow these instructions. So I'm going to show you right now what we're going to do. Here is StatCrunch. I'm going to go ahead and go to Stat and then go down to ZStats. Go to one sample with summary. And it's going to give me this. In the sample mean, I'm going to put down what my sample mean was. In this case, it was $10,672.84. I'm going to put down the standard deviation for the population. So that standard deviation for the population, $15,056.37. Okay, this is all the same information from the example that we did on the restaurants, the one we just got done doing. Remember, the sample size was 30. Why is it asking me these things? Well, it needs to know the sample mean because it needs to know what the presumed population parameter will be. So we're presuming that since the sample has this mean, the population will too. We know the population standard deviation, and we need to be able to divide that number by the square root of the sample size, which is another thing it's asking us, to be able to calculate the standard error. So it's doing all the calculations for you. The last thing you need to do is you need to click on the confidence level that you want. Let's go ahead and do the 95% confidence level first, and we're going to click Compute. It will give you the lower bound and the upper bound here. Okay, let's do it one more time with the 90%. So we're going to go to Stat, ZStat, one sample with summary, and click it. Our information is going to be the same for the sample mean. It's $10,672.87. The standard deviation was $15,056.37. And the sample size was 30. Again, it's using all these things to calculate the standard error and have an idea of what the presumed population parameter is for the mean. Okay, and then we're going to click confidence level, but this time, instead of having it 95, which seems to be the default for StatCrunch, we're going to go ahead and change that to 90. Boom. And it will give us both the 95, I'll put it in order, give us the 95 and the 90, okay, here for us. I've gone ahead and pasted those outputs here for you. It does not give the margin of error, so I've also inserted that here. Notice here with the 90, this is for the 95% confidence. Yeah, here it is. See, 95% confidence interval level. It's got a bigger, right, wider interval. 95 is wider than 90, so the margin of error is going to be longer than the margin of error it is for 90, okay, because it's having to add that number and subtract that number from the sample mean, which we can find right here. So this is really nice because it just kind of lays everything out for you. It's very easy to use, and you have a really clear idea of how to do it using technology. So what's the big idea? Today's big idea is that since the sample is smaller than the population, there will always be some error in the calculations. Confidence intervals establish a range of values within which the true population exists or is likely to exist. The level of confidence determines the width of the confidence level, and it expresses how confident you are that the true population resides within the lower bound and the upper bound. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher, Torres. Stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!